Good afternoon. Thank you, Shannon. Thanks for the opportunity of speaking here at the USDA. I've been instructed not to move beyond this part, so I'm going to be, I usually like to walk around the stage, but I'll try to stay here. This year, we are celebrating the 75th anniversary of the Oak Ridge National Lab, and I would like to tell you something about the history of the lab. And what I'm going to do in this presentation is I'm going to give you a little background to give you information about the national labs, in particular ORNL. I would like to share with you the idea that private-public partnerships can be very effective. And I'm going to show you some examples of success stories. And one of the messages I would like to send is that perhaps when it comes to utilization of coal for making value-added products, there is an opportunity for establishing one of these public partnerships and being successful. Then I'm going to give you some of the justification for why I think this is the right time to pursue some of those ideas. But let's go back to 1939, and this is a picture of Albert Einstein. He had a summer home in Long Island, and next to him is Leo Szilard. He was a physicist from Hungary, and Szilard is not very well known. He's well known in the physics community, but perhaps outside the physics community, you probably haven't heard of him. But he was part of a group of people known as the Martians. And these were 5 Hungarian scientists who were born in Budapest within a square-mile radius. Some of them went to school together, but they were all contemporaries. All of them pursue studies in physics. All of them left Hungary after the rise of the Nazi regime in Germany, and all of them came to the US. Szilard was very sharp, and he's probably the least known of the 5, but he has a patent for a nuclear reactor. So as soon as they knew that the Germans were trying to develop an atom bomb, he saw the potential, and he worked with Enrico Fermi, and they submitted patents for nuclear reactors. But in this particular case, they wanted the US to become aware of recent developments in Germany, where they have demonstrated the ability to split nuclear atoms, to split the atoms, and in particular breaking down the nucleus, which will come with tremendous releases of energy. And because Szilard wasn't very well known and the other Martians were not very well known, they approached Einstein, who at the time was already living in the US, and he was the best known scientist of his time. So they convinced him to sign a letter that they addressed to President Roosevelt. And in that letter, they describe the recent work that has taken place in Germany, and they make a recommendation to start a crash program to make sure that the US develops the bomb before the Germans can do it. And that's really the origins of the Manhattan Project. The other 4 Martians, and let me just say this because the story of these Martians is fascinating. In addition to Szilard, you had Jan von Neumann, who was an active participant in the Manhattan Project. He made tremendous contributions to quantum physics, game theory, computational sciences, and if you pick up a book on any one of those topics, von Neumann's name is going to be all over the place. He was really the father of one of the very first computers that we built in the US. Then you have Theodor von Karman, who helped establish the modern Air Force in the US. You had Eugene Wigner, who got the Nobel Prize in Physics and was the first director of the Oak Ridge National Laboratory. And the other one was Edward Teller, who was also an active participant in the Manhattan Project, and he was the father of the hydrogen bomb. So, you know, what are the chances of having 5 people growing up in a square mile of each other and making these tremendous contributions? I mean, the odds of that are unimaginable. So, but tremendous contributions, and they really, those connections that they had, they really triggered the start of the Manhattan Project. So the scientific headquarters of the Manhattan Project were at the Los Alamos National Lab. Oppenheimer was leading the program. There was a fair amount of activity at the University of Chicago with Enrico Fermi and Compton. And then there were two production sites. One was at Oak Ridge, the other was at Hanford in the state of Washington. In Oak Ridge, there were actually three facilities. Two facilities were focused on separating isotopes of uranium, in particular uranium-235, which they successfully did, and they were used to make the bomb that was dropped in Hiroshima. And as a matter of fact, 3 days ago, we celebrated, it was the 73rd anniversary of dropping the bomb in Hiroshima. The third facility at Oak Ridge was the Oak Ridge National Lab, what became the Oak Ridge National Lab, and it was really the operation of the graphite reactor. The graphite reactor was the first continuously operated nuclear reactor. And the idea of establishing this facility was to demonstrate that if you will irradiate natural uranium with neutrons, you could produce plutonium-239, which happened to be a material that could be used for bombs. And it was that discovery that prompted the construction of the reactors in Hanford. The plutonium from Hanford was used to make two bombs, one that was tested in New Mexico, in Alamogordo, and the other one that was dropped in Nagasaki, which literally triggered the end of the Second War. And today is the 73rd anniversary of that bomb. So those were the origins of the Oak Ridge National Lab, the graphite reactor. Today, we have, as a result of the Manhattan Project and the end of the war, we established a system of national laboratories. We have 17 national labs. Oak Ridge, located in East Tennessee. You can identify some of the other labs. Los Alamos and Sandia, New Mexico. We talk about Hanford up there. The Bay Area, we have Lawrence Berkeley, Lawrence Livermore National Labs. And in this presentation, I want to make reference to a sister lab that has two facilities, one in Pittsburgh and the other one in Morgantown. That's the National Energy Technologies Lab, and we have a representative from that lab here today, so we're happy to see you here, Joe. And I'll mention that because some of the work that they are doing is very connected to the discussion that we're going to have here today. So the Oak Ridge National Lab starts as part of the Manhattan Project. Its birth is connected to war, but today the mission is very different. Our mission is to deliver scientific discoveries, foremost, but also technological breakthroughs that will help us ensure energy and national security in the country. And that by doing that, we'll be able to promote economic prosperity of the nation. And that is an important mission that we have. And towards the end of this presentation, you're going to see why we have put together some ideas that involve economic development, because sometimes we don't associate those with the role of the national laboratories. But that has really become very important. And if you have been following some of the policies in the Department of Energy, there's a tremendous push to make sure that all the inventions and discoveries find their way to the market. And that's something that I want to tell you today. When you look at the portfolio of R&L, it's the broadest portfolio of all the national labs, but we have strengths in 4 areas. One is computational science and engineering, and I'm going to tell you more about that. We have actually the fastest computer in the world. Secretary Perry went to the lab last month to unveil a new machine called Summit that is now running into the hundreds of petaflops. We are already paving the road for the next machine. It's going to be an exascale machine that's going to be 100 times faster. So we have really tremendous strengths in computational science and engineering. We have the broadest program on material science. That's where I work at the lab, anything related to materials. We are the world's capital when it comes to neutrons. We have the two most powerful neutron sources, the high flux isotope reactor and the spallation neutron source that we use to understand the structure of matter. And then we also continue doing work on nuclear science and technology that dates back to the Manhattan Project, but now we're using it to develop, for example, a next generation of nuclear power plants that will be safer and more efficient. We at the national labs don't do a good job telling the public how their dollars get spent and what the impact of those dollars are. In the last few years, we have been trying to do a better job. And this is a slide that illustrates some of the contributions that ORNL has had to establish new industries. And perhaps the greatest impact of all is the industry of radioisotopes. At the end of the war, when we demonstrated that we were able to produce plutonium out of operating a reactor, we started using those facilities to produce radioisotopes mainly for metrology and medical applications. And that industry started at the Oak Ridge National Lab. And we're very proud of it. And obviously, that's a multi-billion-dollar industry that was established as a result of the lab. All the nuclear fuel processing had its start at the lab. And this is a large industry. Something that you may not know is that every boiler that we have in the US burning either coal or natural gas has a tubing and pressure vessels made with an alloy that we develop at the Oak Ridge National Lab. It's an iron-based alloy, it's a steel that has 9% chromium, 1% molybdenum, and that is the most widely used alloy to make boilers and tubing for fossil fuel power plants. That was developed at the lab. Okay? And one thing I would like to say is that if we get together in 10 years, if the USDA invites me to give a seminar in 10 years, I want to say that we will probably trigger a new industry based on the use of coal to make value-added products. That will be a multi-billion-dollar industry. Okay, so I hope I can come back and we'll test that prediction. We truly believe that this is a great opportunity. Let me talk about rare earth elements, and I'll do this for two reasons. One, because there is a connection between rare earth elements and coal, and this is going to become everything here. But the second one, because I want to talk about private-public partnerships, and I want to talk about one of the innovation hubs that was established with several national labs, including ORNL, to address the availability of rare earth elements. I don't know if you remember, but back in 2010, a series of events happened very quickly. And it started when China started to control the export of certain elements. And these elements are known as rare earth elements. And I'm going to tell you that they are really not that rare, and we'll talk about here in a minute, but they are very important because they are used in a broad range of applications. So summer of 2010, China starts controlling the export. Lots of activities and promulgations by the Chinese government. Japan, that depends a lot on these, raises red flags. Everybody starts getting pretty nervous by the fall. The U.S. realizes that it's very vulnerable to the availability and potential shortages of rare elements. So red flags and alarms go throughout the federal government, not just in DOE, but the Department of Defense as well. And it's then known by China has been acquiring mines throughout the world, and they really have pretty good control on the supply of these rare elements. And by this time, we had already closed a mine in Mountain Pass that was one of the largest producers of rare elements, and by then it was closed. So China had really, at that point, control of the availability and supply of rare elements. So these rare elements, if you look at the periodic table, if you remember your chemistry in high school, there is a group of elements known as the lanthanides, and if we add yttrium to that, those are the so-called rare elements. Okay. You have lanthanum, cerium, praseodymium. Neodymium is one of these incredible elements, and you're going to see why. And then you have things like gadolinium, europium. These are fluorescent lamps, so they rely on europium to get white light. So these elements are very critical for many technologies. This is a chart produced by the US Geological Survey. And on the horizontal axis, you have atomic number. So you go from hydrogen 1 all the way to uranium 92. On the vertical axis, you have a logarithmic scale, and it's normalized by the concentration of 1 million atoms of silicon. Okay. So if you look at silicon, which is element 14, everything is normalized to the amount of 1 million atoms of silicon. And silicon is one of the most abundant elements on Earth. You go to the beach, the sand is pretty much silicon and oxygen. Oxygen is everywhere on the surface of the earth. And by the way, these are values of concentration from the surface of the earth. You look at hydrogen, you have lithium. You know, compared to silicon, lithium is not that abundant, and we are relying on lithium for energy storage devices. Then you have carbon, magnesium, aluminum is plentiful. And then you go through the transition metals, you have iron, copper, nickel. And then you have your lanthanides over here, which are rare if you compare them to silicon, for example, or some of the transition metals, but really not that rare. I mean, they're still relatively abundant. The problem with these rare elements is that if you find them in a very dilute concentration, and that's really the challenge. But they're really not that rare. The really rare elements are here. Palladium, rhodium, tellurium, gold, platinum, osmium, iridium. This is why, you know, if you get a jewelry, it will probably have gold or platinum because these are really precious elements. I'm a Delta frequent flyer, and Delta has its level of loyalty based on precious metals. So if you have silver, you're almost nobody there. And if you're gold, you know, you can get to work with some 2 or 3 or 4, and then if you're platinum, it gets really better. They have the diamond category, but you know, that's an allotrope of carbon there. And I was telling somebody at Delta, said, you know, if you guys really want to have the very elite members of your frequent flyer category, give them the iridium category. You know, that's really rare. This is the rarest of the rare elements. And just as an aside note, iridium is a refractory metal, has a very high melting point. It's very difficult to process, but we at the lab have found ways to make capsules. And we use these capsules to encapsulate isotopes of plutonium. There's an isotope of plutonium. We talk about plutonium-239 to make the bomb. Okay? There's another isotope, it's plutonium-238, which we use for radioisotope thermoelectric generators. So if you have seen those pictures coming of the New Horizons probe when it passed through Pluto, or if you see the pictures coming out of Saturn and Jupiter by the Cassini probe, if you see the pictures coming from Mars, from the Curiosity rover, all those devices are powered with a radioisotope thermoelectric generator. It has a few pounds of plutonium-238, releases a lot of heat. We have these thermoelectric materials, they convert the heat into electricity, and then they provide electric power for these devices to operate, okay? And we use iridium to encapsulate the plutonium. And that's a very unique application. It's very expensive, only NASA and some of the national security applications can pay for that. But this is truly the rarest of the rare, iridium. So here are the lanthanides, and these are the elements that we're going to talk about for the next couple of minutes. You may have seen some of these slides. This is an example of where these rare elements go into applications. And if you think about the electrification of transportation, and we're really at the tipping point, you know, when we, 10 years from today, we're going to be looking at 2018 with Tesla getting the $5,000 car production per month. That's really going to be the tipping point. And every one of these electric cars has an electric motor. And those electric motors rely on a permanent magnet that has neodymium and dysprosium primarily. Okay. It was because of neodymium and dysprosium that we have cell phones with a small earplug. The ability to miniaturize these devices, speakers and microphones, was because of our ability to produce very strong magnets. Those magnets depend on elements like neodymium and dysprosium. So when the Sony Walkman, some you guys are probably too young to remember the Sony Walkman, but the Sony Walkman came in, it had a tape, it had these headphones, and they were relatively small. I mean, it was a true novelty. It was because we were now producing small speakers using neodymium iron boride magnets with some dysprosium. That really made a big difference. And obviously, the ability to make a compact motor for transportation is very, very important. Internal combustion engines have an oxygen sensor that uses yttrium, and that is important to control the operation of the engine. Most glasses rely on cerium for production. If you look at these are batteries for some of the Toyota products that rely on elements like lanthanum for the cathode. Internal combustion engines rely on catalytic converters that have some of these elements. So you can go through the list, and these elements have a lot of applications. If you want to open your car remotely, you're going to have an electric actuator that's going to have neodymium magnets. So neodymium is really one of the most important elements, and we rely on that. This is just an example of a car. If you look at a military platform, maybe a fighter jet, the amount of magnets and actuators that you will find is just astronomical. So this is not just civilian applications, but also when this crisis erupted in 2010, DOD raised red flags and became a national priority. We talk about portable devices, whether it's the camera, the battery, the speakers. These are examples of how some of these elements get utilized So 2010, the government reacts. Secretary Chu commissions a report with a strategy to address the supply and availability of rare elements. This is a snapshot of the analysis that went into that report. They created plots where they plotted on the horizontal axis supply risk from 1 to 4, 1 being low, 4 being high. And then in the vertical axis, importance to clean energies. 1 being low, 4 being high. So as you go to the upper right corner of this diagram, that tells you these are the elements that we have to pay attention to. And look at the list. Neodymium, we talk about magnets, actuators, yttrium, not just for oxygen sensors, but we also have fuel cells, solid oxide fuel cells that use zirconia stabilized with yttrium as the electrolyte. Europium for your lighting, terbium and dysprosium for magnets and other applications. And then we saw some other elements that were lanthanized that were not that critical, but the red ones are the ones that were considered really critical. So the report, at the end of the report, there are a number of recommendations, and it's really a three-leg approach. On one end, they said we really have to look at the new mining and separation technologies. We should really reconsider the closing of Mountain Pass, address all the issues with mining, environmental impact, and we really have to pay attention to that as one approach to the strategy. The other one was substitutes, and this is a challenge to the national labs. Why is neodymium so good for magnets? Why is yttrium so good for stabilizing zirconia for electrolytes for solid oxide fuel cells? Those are scientific questions. So the challenge to the labs, and you will see it here in a minute, was, can you tell us how could we replace some of these elements? Are there other elements in the periodic table? There are 92 elements in the periodic table. Could we replace these elements with other elements? And the answer is, well, we need to understand the role of these elements, and once we understand the scientific mechanisms, the physics and the chemistry of that, we may be able to come up with substitutes. So it's a challenge that we take on the lab. And then the other one is recycling. Rather than tossing something to the trash, can we recover, for example, from hard drives on computers, the rare elements that are in the magnets that make the hard drive spin? Same thing for the catalytic converters. And so there's a number of activities focused on better recycling approach. So these were the elements of the strategy that the Department of Energy developed in response to that crisis of 2010. I told you about the need for replacing elements, and this was an open challenge to the national labs. So the DOE had a competition for an innovation hub to address these critical materials. And at the end of that competition, a team that was led by, that is led still working by the Ames National Lab in Ames, Iowa, ORNL is part of that team, came together with a plan to look at recycling and substitution. And there are some elements on mining and separation as well. And this is a picture from one of the first all hands meetings that took place. And if you go through this, through the document that they put together in the winning proposal, their focus was, let's look at the disruptions on the supply chain. Let's look for substitutes. Here's where science comes into the picture. And then this is an engineering and chemistry problem. What can we do to improve recycling? Okay. So pretty much they read the document, the strategy, they put together a plan, and then they got funding to do the work. This has been a very effective, successful partnership. To date, a lot of invention disclosures, a lot of patents, a lot of papers, but most importantly, the industrial participants in the Critical Materials Institute are taking the discoveries, the inventions, and they are commercializing them. And that's really what we want to see. This is one of the important aspects of this activity. It's not just writing papers. You know, you have a lot of scientists who are very happy just writing papers. It's really how do you translate all of that into the private sector and into the market. And this is a diagram that shows you all the participants in this Critical Materials Institute, again, led by Ames, but you have Idaho, Lawrence Livermore, and Northern as participating labs. Then you have universities, Iowa State, Purdue, Rutgers, Colorado School of Mines, Brown. Then you have industry, you have GE. You have people who work on mining, separation, Rio Tinto, companies that make magnets like the Electron Energy Corporation. EC is making new alloys using byproducts of the separation of these rare elements. Arnold Magnetic, obviously they make magnets. So very effective partnership between the private sector and the federal government. And then you tap into your expertise across the national labs, universities. And then you have the supply chain from mining to production, and then the integration of all these products into systems. So that's the message, the first message I want to send. We have a strong track record at the labs of forming strong partnerships with the private sector to deliver on promises, okay? And that's exactly what I was saying. You know, this is a good example of a successful public-private partnership. Now, let me say something else, and we're going to transition into coal, the transition to coal. Our colleagues at the National Energy Technology Lab have a number of programs and projects that are focused on recovering rare elements from coal and coal byproducts. And this really came, somebody was doing an analysis of fly ash. You know, when you burn coal, you collect the ash. Sometimes you have these ponds next to the power plant. You let the ash there to sit for a long time, and eventually it may be buried in a field. And while doing the chemical analysis of the ash, they found relatively high concentrations of rare elements. And elements like neodymium, dysprosium, the elements that we talk about. And sure enough, when they started looking at some of the reports from the U.S. Geological Survey, in additional studies, they found that there are many coals, in particular in Appalachia. And I have to say that because not all coals are the same, okay? But there are some regions of Appalachia where the concentration of rare elements is relatively high. And the NETL, the National Energy Technology Lab, started a number of projects. These are some of the projects and the participants. And they have been very successful. They've been able to start with concentrations of 500 parts per million, which is relatively low. And through chemical processes, they've been able to increase the concentration into single digits and beyond. So this is another strong example of good success stories when the national labs work with industry and academia. And a lot of good technologies are going to come out of this. But these are ongoing projects. And they have some very challenging targets of increasing the ability to separate and increase the concentration of these rare elements out of coal, okay? And I know you had a seminar not long ago. A professor from West Virginia came and talked about some of these projects. So kudos to NETL. They're doing a fantastic job, and we'll see more of this in the near future. So that's a transition to code. Okay, we talk about rare elements. What I really wanted to highlight was the ability of the national labs to work with the private sector. In academia, we talk about rare elements as an example, the Critical Materials Institute. Now let's talk about coal, and not just coal as a fuel to produce electricity, but coal as a precursor to manufacturing value-added products. Now, some of you may say, "Oh, come on, Edgar, you know, we've been making products out of coal for 100 years. I mean, what's new about this?" And you know, I have to admit, this is not a new idea. We have seen versions of this. This is known as the coal tree. Okay. And if you look at these branches, you see coke and coke grease, like oil, gas, tar, and you can go to the branches and look at cosmetics. And so we've been at this for a long time. And it was actually in 1991, there is the German equivalent of Life magazine. They had a coal tree. It's in German. But, you know, Germany has had a great success using coal to make liquid fuels, for example. But it's an example of how they had already discussed the ability to use coal as a precursor, mainly for chemicals, okay? Mainly for chemicals. And then here in the US, you can, you know, there are evidence of this idea. So what I'm telling you today is really not new. You know, people have been talking about using coal as a precursor to make value-added products. In this particular case, it's mainly chemicals. But there is something that is really different and is relatively new. And that is the collection of tools that we have established at the national labs in some universities. Those tools did not exist 75 years ago. And what I would like to tell you today is that those tools, if employed, will allow us to take some of these ideas to market very quickly, because the power of these tools is just incredible. We can start with supercomputers. I told you about Secretary Perry unveiling Summit at Wattenell, 130 petaflops. I mean, if you think about these, kiloflops, megaflops, gigaflops, teraflops, petaflops, exaflops, 1,000 times. When I got in grad school in the late 80s, early 90s, the idea of running a machine this fast, it was just unthinkable. And this is only 25 years ago. Today, we are talking already exascale computing. And not only that, the architecture of these chips, which is a combination of a CPU and a GPU, a graphic processing unit, which actually produced by a company called NVIDIA, which is a supplier of chips for the gaming industry. I mean, these chips are fantastic. They provide a platform for artificial intelligence. So it's not just having the power to crunch numbers, such as solving Schrodinger's equation, quantum mechanics to understand the interaction of electrons and materials, but also to do materials discovery if we can provide enough information into this. We have electron microscopes capable of imaging single atoms. Think about it. You know, who has a background in physics? Ludwig Boltzmann, yeah. Austrian physicist. If you open up a book in thermodynamics, solid-state physics, Boltzmann's name pops up almost in every page. I mean, that guy was spectacular. He grew up in Austria, worked in Germany, tremendous guy. And he believed in atoms. Now we're talking about 1860s, 1870s through the 1910s. And there was a group in Germany led by a fellow named Ernest Mach. This is the guy who coined the Mach number, which is the ratio of a speed to the speed of sound. So Ernest Mach was a very influential physicist in Germany, and they made fun of Boltzmann. You know, whenever Boltzmann went and talked about molecules and gases and the speeds and distributions, they made fun of the poor guy. The problem with Boltzmann is that he was a very sensible guy, and he got depressed. And it got so bad that he killed himself. 1906. This is just about the turn of the century with the quantum revolution. You have Planck talking about quantum physics, Einstein talking about quantum physics, Brownian motion, photoelectric effect, and then everything that can be after that. But Boltzmann killed himself. You know. And we established a microscope at the lab probably in 2002 with the ability to resolve 0.7 angstroms in spatial resolution. If you think about the distance between atoms in a crystal is 2 or 3 angstroms. So by being able to resolve 0.7 angstroms means that you can literally see single atoms. And then we have these detectors that can collect X-rays and electrons. And it's not just a matter of seeing single atoms, but we can tell you what type of atom it is. Oh, that's an atom of gold. That's iridium. That's platinum. We have that ability. And, you know, and I wish I had a time machine to be able to go back to 1906 when Boltzmann killed himself. Say, hey, buddy, don't do it, man. Atoms do exist. You know, we have seen them hanging there for another 20 years and, you know, keep on writing papers. Imagine if Boltzmann had lived for another 20 years. I mean, the guy was incredible. So we have those microscopes. And the reason why I mentioned this is going to become evident here in a minute. We also have developed equipment where we can put something on one end, and then we have chemical analysis, molecular structure on the other end, and we can do it fairly quickly. And then we have very powerful light and neutron sources. I told you about the neutron source at Oak Ridge, where we can study the structure of matter at the atomic level and give you a picture representation of how molecules are structured in 3 dimensions. And the argument that I would like to make is that if we use these tools, we may be able to understand, number one, the structure of coal. And remember that all coals are different, because by understanding that the structure, we may be able to come up with ways for breaking down coal from these big molecules into smaller molecules. And in the process, we can recover the rare earth elements, but then do something else with the rest, okay? And that's gonna be enabled by having access to this very unique tool. So this is true. You know, if you dig coal out of Appalachia, it's going to be different from the powdered PRB, the powder riven basin in Wyoming, and it's just like wine. I mean, you say wine. Well, let's talk about wine. What type of wine? White or red? And even if you say red, well, the Cabernet, the Rioja Tempranillo. This is the same for coal. Not all coals are made the same. And most of our understanding of coal is based on the structure of coal for power generation. There's been a lot of work, believe me. I mean, if you review the literature, a lot of information about the structure of coal, but all of those studies were focused on our ability to burn coal to produce electricity. And there are some gaps there. And those gaps are important because if we can understand the structure in a very holistic way of coal, we're going to be able to do some of the things I'm going to show you here in a minute. Even in 10 years, you know, this is a paper published in 2002. And that was a very influential paper because it was one of the very first attempts to provide a molecular description of coal. And these are all 2-dimensional models, okay? These are all, these hexagonal arrangements are carbon. On the plane, you have hydrogen and oxygen. This was a very influential paper, 2002. In 2012, Professor Jonathan Matthews from Penn State developed a model, 3-dimensional model, where using advanced characterization tools, he was able to provide a 3-dimensional molecular description of coal, okay? And he did that fairly quickly. He applied a number of techniques, optical techniques, electronic techniques, spectroscopic techniques, and now we have these 3-dimensional representations of coal. If we could do this with every type of coal, you know, we can pretty much following a genomic approach, get a very good description of all of these materials. Because once we have that description, then we can start asking questions. How many different ways do I have to break down these molecules? And can I find the most energy efficient and cost-effective way of doing it? Because if I break down these molecules, I can get all my benzene rings with a certain number of molecules, and I can use those to make this product. But then there are going to be some leftovers that I can send to another stream to make other products. And by the way, I can get the rare earth elements as part of these products. This is what we are talking about. We didn't have these capabilities a few years ago. Now we can do this type of analysis with high fidelity. And the way you do it is through something that we call quantum chemistry. With quantum chemistry, you can start asking those questions. You know, if I have this array of molecules, how many different ways can these molecules be twisted? And if you know every link in that molecule that has an energy value that is needed to break it, how many different ways do I have to break it down? And you can ask the computer to do those calculations in a millisecond. Okay? So we have the capability to do it. And it is not just the brute power of the computer, but it's also the theory that comes behind it. We have made tremendous advances in quantum chemistry over the last few years that we can do those type of questions. So we can start asking questions. I would like to have a small ensembles of molecules. How many different ways do I have to go from here to here? And then the computer is going to tell me, okay, you got to heat up at a rate of 10 degrees per second, up to 300 degrees C, hold there for 5 minutes, quench down, do something, and voila, you have this. Okay? And we can ask all those questions, and the system is going to give us the correct answer. So let me tell you what I envision for this. What we really envision is something called a coal refinery. It is equivalent to a petroleum refinery. You know, it's pretty much the same idea. Where on an idealized set of conditions, you will establish this at the mouth of a coal mine. Okay. And once you have answered all those questions, you can start removing elements that you don't want in your stream: mercury, arsenic, sulfur. You can recover water. I mean, if you get coal out of Wyoming, it has about 20% water concentration. And that water could be used for industrial processes, for irrigation, secondary processes. So that's another value added that you get in certain types of coal. We talk about the rare elements. Can we get them out? And then use them for all these applications that we discussed. Obviously, there are going to be some leftovers, and those could be used as chemicals. We could make activated carbon. You know, we have a water availability problem in certain parts of the world. There's a lot of water on the planet. It's a lot of water, but you may not be able to drink all that water. So how do you remove impurities or salts? How do you desalinate ocean water or brackish water? And you can do that with activated carbon. You can get that out of coal. We can tailor the structure of carbon to make what we call mesoporous membranes for separations, not just for water purification, but for any number of chemical processes where you need to separate. If you look at the chemical industry, separation processes are some of the most energy intensive processes available. And we can template carbon to have certain characteristics of porosity, surface chemistry to be able to do this separation processes in an effective way. Mm-hmm. Metallurgical coal, this has been on the news the last several months. If you look at how we use coal in the US today, we produce something close to 700 million tons of coal a year in the US, at least in 2017. 93% of that coal goes to produce electricity. About 3% goes to metallurgical processes, mainly for steel. If you look at blast furnaces, you gotta use coal to make steel, or for producing aluminum. So metallurgical use of coal are very important, and we can get it as part of this process as well. Carbon fibers. Okay? And I'm gonna take a step here in carbon fibers because ORNL has really become the carbon fiber capital of the world. Okay? Have you heard of Greg LeMond, cyclist? Tour de France winner 3 times. He just established a company right in Oak Ridge next to our, we have a building called the Carbon Fiber Technology Facility. We established that one in 2009 as part of the ARRA program at ORNL. And Greg LeMond said, I'm interested, I want to license a technology that ORNL has developed to make low-cost carbon fibers. So he just established a factory next to us. he wanted to hire all the technicians that were working in our lab, and we said, wait a minute, no, not that fast. But we're going to work with him, and he wants to start making bicycles with these low-cost carbon fibers, but he sees the auto industry as the biggest prize down the road. This is going to be a way to get into the game. So you probably have heard about carbon fibers. There are many ways to make carbon fibers. Today, there are probably 6 different routes. You can use rayon or lignin. Shannon worked at Vito, so she probably recognizes there lignin as a potential precursor for carbon fibers. But today, most fibers are made out of a chemical called polyacrylonitrile PAN. And that's the same chemical that we use to make carpets. Okay? If you look at the fibers of carpets, that's the precursor that we can use to make carbon fibers. There are companies that make socks out of PAN. So we use the same fibers and we can convert them into carbon fibers. You can use petroleum or coal to get a compound called pitch, which is can be extracted from coal. You can make carbon fibers that way. So this is what we are interested in. How do you use coal to get this compound pitch as part of this separation process that we talk about, and then how do you take pitch to make carbon fibers? So let's do the numbers. We talk about value-added products, and here is where people really get interested here. You can buy a ton of coal for about $50. If you go to Wyoming, you can pay probably $15 for a ton of coal, okay? Coal from Wyoming is much less expensive. Today, if you make a ton of carbon fibers, you could sell them for $20,000. Okay? 50% of the cost of carbon fibers today is connected to the precursor. If we use coal, and we're doing the numbers, I'm going to say something here about that in a minute, about the techno-economic analysis. There's a tremendous potential to realize a big return on investment in the case of carbon fibers. And obviously, we continue to do research at the lab. We have a number of projects where we have a target of $10 to $14 a kilogram for carbon fibers. And we have been talking with the OEMs in the auto industry for the last 15 years. I remember the OEMs got together and they created an organization called US Car and another one called US Drive. And the idea was to work together for pre-competitive technologies, working with the national labs. And I remember those discussions. They say, if you guys can make carbon fibers for $30 a pound, we'll be very interested. 2 years later, say, okay, we are making carbon fibers for $30 a pound. Well, it's not good enough. Can you guys make them for $15 a pound? And then they'll go away and we'll come back and say, okay, we got estimates. If we do this, $15 a pound, and they kept on lowering the bar. Now their last targets being $7 to $10 a pound. And we have the technology using PAN and some modifications that we have made to the furnaces to do it. And with coal, we are going to be able to make those targets without any question. So, and this is going to be the biggest market for carbon fibers. By the way, the Japanese, in this case Mitsubishi, you can buy for almost $1,000 a kilogram carbon fibers from they use petroleum to make those fibers. This idea of pitch-based carbon fibers is not a dream; it's a reality. And the goal here is create technologies that will allow us to lower the cost so that they can be used in the auto industry. Now, as I told you, we are not the only ones doing this. We keep track of the literature and the number of papers coming out of China on this subject. It's astronomical. I mean, if we don't get our act together, we're going to be buying carbon fibers from China. Imagine I mean, I will cry if we have to buy coal-derived carbon fibers from China. I mean, that'll be, but we have people in China, and a lot of times when you are developing new technologies, you don't publish. The fact that these people are already publishing some of these should tell you something about that. The Spaniards have been working on this for a while. Another paper from China. So a lot of activity in this area. A lot of the information that we used to get from China was pretty bad, 15, 20 years ago. The quality of the papers coming out of China has gotten better and better. So we really have to take this challenge very, very seriously. Obviously, there are great success stories using carbon fibers in the structures. This is probably the greatest success outside the military platforms. The 787 is all fiber reinforced composites. Okay, and this is a way they make the fuselage, and it's all carbon fibers. The wings, a lot of carbon fibers in the wings. So the market is large. But this is really the biggest prize, the auto industry. And there are companies like BMW. There are some exclusive models where, in some demonstration models, where they have used all carbon fiber technology to make the chassis. This is the small i3. It's all carbon fiber reinforced composites. Okay. And the benefits for using carbon fiber composites are clear. They are lightweight. When you divide the modulus, the elastic modulus by density, or the strength by density, or the amount of energy that you will absorb during a crash-like scenario over density, they beat the steel and aluminum by far. So all the benefits for using these materials are there. People continues to develop technologies for repair, for joining, which are key challenges when you manufacture complex structures, and a lot of those challenges are being overcome or have been overcome. So this is an example, and this is really where the greatest impact, in my opinion, in the near term is going to be if we can get carbon fibers, low-cost carbon fibers, into the transportation, the highway transportation technologies. If you look at the market analysis for that, that is also their opinion. This is a snapshot of 2014 with predictions for 2020. Obviously, the aerospace and defense industries depend on these materials greatly. If you look at pretty much every bomber or fighter, it's all composites. Wind energy, we have been using glass fiber reinforced composites for the blades of these massive wind turbines. If you increase the diameter of the turbine, the amount of power goes up with the square of the radius of the turbine. So we have pretty much reached the limit of how far glass fibers can go. Carbon fibers are stiffer than glass, meaning that you can get longer blades, and by doing that, you can improve the power generating capacity of wind turbines. Obviously, we talk about sporting goods, bicycles, rackets, skis, but that's really the biggest prize for some of these technologies. And this is an area where O&L is really heavily focused. We have a number of activities here in carbon fibers. The other thing that, and you may have heard of graphene. Graphene is a form of carbon. It's a single layer of graphite. If you remember your lead pencils, that's graphite. If you could slice one atomically thick layer, what you will have is graphene. And these materials, when you lower the dimensionality of these materials to single atomic layers, the properties are just incredible. You're going to see in the market in less than 5 years screens made out of graphene. Right now, the limitation is the ability to grow single crystals of graphene big enough for these screens, but pretty soon you're going to see the whole wall with graphene, with the intensity of the colors, a fraction of the energy required to operate. I mean, this is coming. So remember the graphene in the not so distant future. Graphene has also great optical properties. There are people using for biomedical applications, skin grafts and scaffolds for growing tissue, the electronic properties, and there's some conditions graphene can be superconducting. I mean, this can be obtained out of graphite. The other thing, and this is actually there's an irony on this. You can tailor carbon, and you can get a superconductor, or you can have a material that is an electrical insulator. That's the beauty of carbon, that if you can play with the atomic arrangements, you can tailor the properties from being a superconductor, an insulator. And there are people who have made photovoltaic cells using carbonaceous materials. And this is actually very exciting. Back in 2012, Scientific American published a report talking about carbon-based photovoltaic devices. This is a paper from a group at MIT. We actually working with Professor Grossman, where they took various forms of carbon nanotubes, graphene. They got an efficiency of 1.3%. Okay, that's not very spectacular. The best photocells today are getting pretty close in the mid-40s conversion efficiency. They're very expensive. But even if you can get it to 10%, which is very possible, this was their first shot, and they got 1.3%. You could get this to 10%, being so inexpensive. The impact of this is going to be tremendous. Somebody did a study, and the study was postulated along the following lines. How much time will it take to mine enough materials to produce enough photovoltaics to generate all the electricity that the planet will need by 2050? Okay? And the amount of power that you need is something like 14 terawatts of power for the whole planet. So the question was, how much time will it take to mine enough materials to make enough photovoltaics with an efficiency of, let's say, 20% to power the entire planet by 2050? Okay? So on the horizontal axis on this study, they had the different types of photocells. On the vertical axis, they had a logarithmic scale with time. So they started with silicon. Well, if we mine enough silicon in 7 years, we can produce enough material to make enough photocells to power the entire planet by 2050. Then they went to cadmium telluride. And if you remember when we showed the plot of abundance of the elements, tellurium was kind of low. So 120 years, it will take you to mine enough cadmium telluride to make enough CDTE photocells. There's another class of cells called 6, copper, indium, gallium selenide, 120 years. Then they went through all the technologies, and then at the end they had carbon-based photocells, 6 minutes. So at today's production rates of carbon, with 6-minute production equivalent, we will make enough photocells to power the entire planet by 2050. Just think about it. Think about the potential of that. And some of this early research work is very exciting, but this really shows the potential of some of these technologies. And it's not just MIT. There's a group at Stanford that has done exactly the same. These are all carbon-based solar cells. They use graphene. I told you about graphene. They're using carbon nanotubes, bulky balls. These are all different forms of carbon that you can get out of coal, and then get very exciting results. And this is very early research. Just imagine, yes, ma'am.
What was that 1.3% on the efficiency?
That was the conversion efficiency of the photocell. So the best cells today are getting pretty close to 50%. And these are structures where you have multi-layer structures, where each layer absorbs a part of the solar spectrum. So by doing that, you can really get up to. There is a theoretical limit for a single wavelength, which is in the 20s. But by doing this, you can get there. But you know, it really takes a lot of effort and cost. I mean, those are very expensive. This will be, you know, this is the type of thing that you will go to Home Depot and paint the walls, the roof of your house, the parking lot, and you know, these things will be relatively inexpensive. But even if they didn't last for 100 years, you could replenish them, and they would be relatively inexpensive to produce. So again, this is very exciting. This is very exciting. So that goes for electronic devices. Thermal insulation, thermal conduction. As I told you, the beauty about carbon is that you can tailor the properties. You can make it to have certain optical properties, and I'll show you some examples. You can build structures that are thermal insulating. You may be able to replace the pink stuff that you put in your homes for thermal insulation. Okay? Or there may be some applications where you want the ability to remove heat very quickly. And we have developed structures at ORNL where the materials have very high thermal conductivity, close to 1,000 watts per meter Kelvin, which is an extremely high value. But you can do this. In fact, there are some detectors at CERN where this was the experiment where they detected Higgs boson. And they use graphite foam developed at Waranel with very high thermal conductivity to pull down those detectors. Okay? That's the beauty of carbon, that you can really tailor the properties. This may be some unique applications. This could be high volume. And again, see how much insulation we use every year in the US. Another tremendous application, energy storage. We're in the midst of the electrification of transportation. I think we already went past the point of no return. But for this to be possible, we really have to have batteries that can store energy. And when we do research on batteries, there are 5 things that we pay attention to. The first one is safety. The last thing you want to see is a picture of a car on fire on the highway. So safety has been the #1 topic when it comes to energy storage research. The second one is energy density, and that is the ability to store electrons or energy in a small volume. And obviously we want to maximize it because energy density transfers into miles per charge, okay? So the more energy you can store in your battery, the longer you're going to be able to drive. The third component is power density. Can you charge your battery in 5 minutes instead of 8 hours? The fourth one is cost. Nobody's going to adopt these technologies unless they are affordable. And the fifth one is durability. Can you make batteries that will last for 10 years or 20 years for your car? These technologies are not going to fly if you have to go to the dealer to change your batteries every year. Okay, so those are the 5 aspects. And in the case of energy density, one of the key parameters is the materials that you use in the anode and in the cathode. So in today's technology, we rely on carbon to be used as the anode material, okay? And the capacity of the battery depends on the structure of that carbon. So for a Tesla, Model S Tesla, there are about 54, 55 kilograms of graphite in all the batteries, okay? And this is a projected cost or price for that graphite. So by 2020, the project is you're going to get pretty close to $4,500 for a kilogram of graphite that goes into energy storage device. Imagine if you pay $12 a ton to make that material. You're talking about orders of magnitude here, at least 100 factor from the cost of the raw materials to the price of the product that goes into, in this case, energy storage. And it's not just cars, but it's laptops, cell phones, portable devices. So this is a great opportunity for graphite. And again, graphite can be obtained from coal, and this will be a tremendous application. Portable devices are now, if you want to get a chemical analysis of your iPhone, there are 30 grams of aluminum. The casing is pretty much the largest contributor, and some of the wiring. The second largest contributor is carbon. You think about it, There are some plastics for the printed circuits. You have carbon for the batteries. Then you go through the other elements. Cobalt goes in the cathode of the battery. You got nickel that also goes in the cathode of the battery. If you get the equivalent price of that, you pay about $7,000 a ton of these elements when it goes into a battery. And, the starting material will be $12 a ton. So when we talk about high value-added product, that's exactly what we are talking about. And the other application, and here is where we see the greatest volume. A lot of times people say, well, we are producing 700 million tons of coal a year. Are we going to be able to use all those 700 million tons to make products? And the answer is probably going to be no. I don't think you can make enough products with that amount of carbon. But just think about how much material goes into asphalt. Today we rely on petroleum, on the tar sands from Canada to make asphalt. What if we use coal to make asphaltene that can be used to make asphalt? And pave every road in the US as part of an infrastructure program using coal. What about shingles for roofing applications? Okay. Again, we are never going to get to the same volumes of utilization when it comes to power generation, but there are some relatively high volume applications. And the whole idea of this schematic, the reason why it is structured this way, is that we want to make sure that we utilize every molecule that comes out of the mine. You know, if there is one message I want to send, give to you today, is the fact that by using science, we're going to find a way to use every molecule that comes out of the mine. Some molecules are going to be rare earth elements. Some will go to make carbon fiber. Some will go to make photovoltaics. The bottom of the barrel will go to make construction materials, the least fancy, technically challenged materials. But we want to use every molecule that comes out of the mine. And the only way we're going to be able to do that is if we use our computational resources, our quantum chemistry, and we ask the question, how many different ways can I break down this big molecule into smaller molecules? And what is the most energy efficient, cost-effective way of doing that? Implement it. And remember that not coals are the same. So some formulations may work well for coal coming from Wyoming. Some may be different for some coals coming out of West Virginia or Kentucky. But you can adapt that on your refinery depending on what you're putting on one end. But the economics are really going to come together if we pursue this approach. Everything that comes out of the mine is utilized. No waste behind. And there should be a product that has value coming out. We started with a letter that Einstein wrote to Roosevelt. I am not Einstein. And just like Silara, I'm probably very unknown in the political circles. But the message that we want to send, and DOE has been a great sponsor and supporter of these ideas. We approached DOE and told them, we have some ideas. We would like you to listen. And one of a program manager named Bhima Sastry, a strong supporter of this work, helped us organize a workshop. We get together in Pittsburgh back in April. We have 100 people from industry, academia, national labs, and we structured the workshop in a way that we wanted to identify the priority science needs and research directions that we had to pursue to make these ideas a reality. And we're in the process of writing a report, so this report is going to become public fairly soon. And we want to thank Bhima and Regis Conrad. Regis Conrad and Bhima Sastry, the fossil energy program, have been tremendous supporters of this work. So we are preparing a report, and it's going to become public in the near future. And again, it's going to outline where do we have to make investments on the science side to accelerate the development of these technologies. The other thing that we are working on right now, my colleague Sujit Das at ORNL is preparing this report. He's doing a techno-economic analysis. And this is very important because we have a lot of phone calls. You know, investors call the lab, hey guys, we would like to invest on these call to products. Who should we talk to? And before we even entertain those type of discussions, it's going to be very important to make sure that we have a very robust techno-economic analysis. Nobody's going to be willing to invest unless there is some solid analysis behind it, and that's precisely what we are doing. And the focus of this analysis is not just on products, but how will that disrupt other supply chains? What happens to petroleum? If we decide to start making asphalting out of coal, what happens to petroleum? There are other products, carbon fibers made out of pan. What's going to happen to that industry? Where are you going to manufacture the products? Are you going to send the coal to Texas, or are you going to put a refinery at the mouth of the mine and get your industry there? So that's going to be produced hopefully fairly soon. But this is a very important piece of work, because this is going to give credibility, or perhaps the report says it's all nonsense. The dollars are not there, and then we just close the chapter and move on to something else. But there are people interested there. There's a company called Ramaco Carbon, and we are already working with them. And as a matter of fact, we wrote a proposal to another part of DOE, it's the Vehicle Technologies program, that was interested in finding ways to use various precursors, including coal, to make carbon fibers. So we are working with Ramaco. We're working with West Research Institute in Laramie, Wyoming. Professor Grossman from MIT, I told you, he's making the photovoltaics, but in this case, we are focused on carbon fibers. and also people from the University of Wyoming. So this project is going really well. And Ramaco, if you have a chance, look at some of the ideas and the vision that they have outlined. In fact, they acquire a mine in Wyoming, in Sheridan, Wyoming, and they are making plans to establish a research center next to the mine and having a production facility there along some of these ideas. And they are focusing on things like carbon fibers, using graphene for biomedical applications. So tremendous vision. So, you know, there are people who believe and recognize the opportunity. So this is really happening. You know, coming to Washington, this is, I think, one of the perks of having the federal government in Washington, because you have all these great museums. So I do my business, and if I have time between my last meeting and catching an airplane, go to museums. And one of my favorites is the National Portrait Gallery. And there was an exhibit earlier this year about American workers. It was a great collection of pictures and paintings, and there was one by Norman Rockwell, Mine America's Call. And I want to close this presentation with another aspect of these call to products ideas. And that's the fact that, you know, we have a responsibility at the labs, not just for scientific discoveries and technological breakthroughs, but also to provide prosperity to the nation, okay? Now, we became a superpower in part because of access to relatively inexpensive energy. If you look at the Industrial Revolution and coal, I mean, we are a superpower, and it was mainly because we had access to a lot of relatively inexpensive resources, and a lot of people in coal communities who really gave their entire lives to this. And I think we have a responsibility to do that. So there is another aspect of this discussion that we are pursuing. It's not just the science. You know, the science is great. We're going to be able to publish lots of good papers. Some companies are going to license technology, and hopefully they will make lots of products and lots of money and employ a lot of people. But we just don't want to leave it like that. We really want to make sure that if we were to implement this as part of this public-private partnership, that we do it in a way that will benefit coal communities. I was invited by the Appalachian Regional Commission to give a talk earlier this year, and it was a symposium here in DC. And I talk about some of these ideas and some of the things that the national labs do. And in parallel, there was a session on the opioid crisis in Appalachia. And then in the afternoon, there was another session on challenges, social challenges and unemployment in Appalachia. And I don't know how often you go to Appalachia, but it's like a war zone. You talk to people, you know, the economic base of the community has plummeted, unemployment, drug addiction is really bad. So the question is, what can we do? And I hope that if we were to get these things going, that we will make sure that there is another component whereby, you know, and the ARC, they've been very supportive of these ideas, is making sure that through the ARC, we work with state economic development offices, local community colleges. Can we retrain people who were connected to the coal industry and are unemployed? Can we give them new sets of skills to be able to operate these new manufacturing technologies that hopefully will be established right there at the mouth of a coal mine, okay? So when we talk about these partnerships, you know, this is our vision. Working with our sister laboratory, NETL, in Pittsburgh and Morgantown, West Virginia. And then we're working with companies like Ramaco. We talk about MIT, West Virginia University. You heard from them about the rare earth elements a few weeks ago. University of Kentucky, University of Wyoming, University of Utah, Western Research Institute, Penn State. You know, these are all key players with a lot of expertise on the subject. And we want to make sure that we work together, again, not just to develop the science, the technology, the commercialization, but also connecting to communities in coal regions and giving them a second air, you know, making sure that we train those people, make the investment right there. It will be a shame to mine the coal again and then send it somewhere else to make products. I think the ideal solution, in my opinion, and I hope whomever gets to invest in these ideas will share this vision that we should do it there, and whatever comes out of those localities should be completed products. Not carbon fibers, but composite panels that can be sent to Chattanooga, Tennessee for the Volkswagen assembly line, or to Tuscaloosa, Alabama to the Mercedes-Benz assembly line, or to Detroit to one of the 3 OEMs here. I think that should be the vision, value-added products, completed components, be sent from these communities. So to conclude, I'm a true believer on partnerships between the private sector and the federal government. I think this is a great opportunity. Again, not just the science, but the social and economic aspects, and we are very excited. So I want to thank you for your attention. I want to thank Shannon for giving me an opportunity